Now we will see how to add two n-bit numbers. Okay, so far we have seen how to add only one column, right? That means two 1-bit numbers or three 1-bit numbers. But now we are going to do that for n bits. Example here, 4-bit addition. So how to do 4-bit addition? First of all, we'll see manually. So add 1 plus 1, you get result 1 plus 1 0, carry will go here, and 1 plus 1 0, carry will be here, right? So 1 plus 1 2, 2 means 0, right? So otherwise remember like this, 1 plus 1 2, 2 plus 1 3. 3 is nothing but sum 1, carry 1, right? So 1 plus 1 2, 2 means 0 here, carry 1. In that way, so carry will be propagated, correct? So this is what finally should happen. Now how to do that? So far we have studied only full adder which can add 3 bits like this. This part can be done, we have circuit for that. So this part can be done, we have circuit, right? So finally this n-bit addition is nothing but repetitively applying full adder, otherwise repetitively applying a single column addition, correct? Let's do that. Assume that, let's say, whenever you have 3 bits to add, we have a full adder. So when I apply x comma y comma z to that full adder, it is going to give sum and carry. Already we have realized that circuit. I am going to use that circuit and I am going to show the logic diagram for this 4-bit adder. Okay. First of all, we begin with ripple carry adder. Whatever the example, otherwise whatever the model we are going to discuss or we just discussed is a ripple carry adder. In the ripple carry adder model, what we do is we add these two numbers. You get carry, right? So we along with that carry and we add these two numbers in that way. So we are going to continue this process. That means once you get the carry, we take that carry and we add these numbers. Once you get the carry, we add these numbers. In that way we are going to do. Okay, let's do that. First step, I show again with example 1011 1101. First step, add these two. For that half adder is sufficient, but assume that, let's say, you have only full adders. With full adder also we can do. How, sir? I will tell you. You have to give 3 inputs to this full adder, correct? So symbolically assume that, let's say, 1 bit is carry. Slowly you will understand why I am saying that it is carry. And 2 other bits, let's say x comma y. Okay, so that x comma y are nothing but these two. So let me use like this: a0, a1, a2, a3. So these 4 bits are b0, b1, b2, b3. Otherwise, for good idea, take numbering like this: a0, a1, a2, a3, and b0, b1, b2, b3. Add them. Start adding them. First you want to add a0, b0, correct? Give that a0, b0 here. So what you get? You get sum, right? So sum will be here. Yes, 1 plus 1 0. I want sum. So I am going to cache here. Now you get carry. What you have to do with that carry? That carry has to be applied for a1 b1 addition, correct? So that's why here we need a full adder. Sir, what about this carry, sir? We are only adding a0 b0, right? What about other input? That input carry should be 0. Here you give 0 input for a0 b0 variables, whatever. Example, here in this problem it would be 1 1. So when you give 0 here always and 1 1 here, you are going to get sum and carry. That carry you connect to this full adder. So this full adder is again going to take 3 inputs, 1 input from here, 2 other input from here. They are nothing but a1 b1. So let me erase this part. You get again sum that I want. That is the second bit. You get carry. So that carry is going to ripple over other full adders. That's why we say it is ripple carry adder. It will be like this: a2, b2. You get here sum and you get again carry. Connect that carry to another full adder. So that would be final, right? a3, b3. Then whatever the carry you get, that is, let's say, let's number them. This is, let's say, carry, first carry C0. This is second carry key1 C1. This is carry 2. This is carry 3. This is carry 4. C out, otherwise carry 4. This is also known as C in. Just symbolically. There is no meaning, so there is no significance to names. Don't worry. You can say C out also if you want. This would be the sum, right? Now we'll see. Example, if you have 1011, 1101, what is going to happen? First carry will be here 0. 0, 1, 1 full adder. If you apply, So you are going to get some sum. What is that sum? We know that 1 plus 1, 0. You get carry. That carry will be propagated to this level. So when that carry comes here, this full adder starts working. When this full adder starts working, then, sir, one question here, sir. What is that? That means, so how do you give the signal so that full adder works only when this carry comes? Not like that. So all the full adders, whenever they get signals, so they will be continuously working. But we take the output only at, when we want. Example, do like this. You have timer. At 9 o'clock, you start giving the input. Okay. Now, automatically, once you are sure that you get output here, you wait. Whenever you wait up to this point where, up to this point where some gets a correct answer, if you can wait, then automatically this gives a correct answer. So what we have to do is, at 9 o'clock, we are giving signals here, 0 here, and A0, B0. This is A0, this is B0. This is A1, B1. Only your doubt is when to take the output, correct? I will tell you. A3, B3. So A0, B0, 1, 1. A1, B1, we are connecting 1, 0. A2, B2, appropriately, whatever it is, 0 and 1. So A3, B3, 1, 1. All these inputs are available at 9 o'clock. Just give it them. Then after that, we will be giving 0 here. Okay. So when you start executing this circuit, what happens is, at 9 o'clock 10 minutes, assume that full adder takes 10 minutes of time, just for easy understanding. After 10 minutes, that you should know, because this is your device, we should know the propagation delay of all the signals. So it is like this. In full adder, when you give the input, when you get output, sum and carry, after 10 minutes if carry comes, then this full adder, before that also, let's say full adder is doing something, but that is not relevant for us. When it is relevant, at 9 o'clock 10 minutes, C1's input is right for us, valid. That valid input will be taken at 9 o'clock 10 minutes and it starts working. Before that also it works, but we don't seriously take the output. So that's why there will not be any problem. Then 0, 1 will be added again. So remember one thing, when you have AND gate, if you give input 0, 1, this immediately after, let's say 10 seconds, if it outputs, then this entire continuously for 10 seconds the circuit will be working. But it depends on when you get the output. When you take the output, otherwise when you say that it is valid output. Example, let's say you are giving 0, 1 at 9 o'clock, but output at this moment, let's say 0. But after 10 seconds only, this 0 and 1 will propagate and you get the right output. Example, let's say this is 1. So because propagation delay is 10 seconds, that means how to understand is, after giving input 1, 1, when will you get the right output, or when will you get the related output of this 1, 1 is after 10 seconds. That is called propagation delay. So this 1 and 1 has to propagate through this, and then only this will become 1, but it takes 10 seconds of time. So before that, if you take the output, still there will be some output, that is 0, invalid. Similarly, here also after 10 seconds this carry will give the right input to this full adder. So before that also it works and it gives some invalid data. Don't take it in that way. So assume that every full adder takes 10 seconds or 10 minutes, then 9 o'clock it starts. 9 o'clock 10 minutes, this will be valid. Then after 10 minutes, this will be valid at 9:20. Then for 9:20, so after 10 minutes at 9:30, this will be valid. Then after getting C3, full adder really starts working properly. Then C4 will be correct only after 10 more minutes at 9 o'clock 40 minutes. Similarly, sum at 9 o'clock 40 minutes. I am assuming that when you give the right input to a full adder, after 10 minutes it is going to reflect the output of that related input. If that is the case, 9 o'clock if you give the input, at 9 o'clock 40 minutes you are going to get the output, by assuming that every full adder takes 10 minutes to give the right output, carry and sum. So let me revise it. 9 o'clock full adder starts working, but only after 10 minutes, that means 9 o'clock 10 minutes only we get this carry. If you don't get this carry, this full adder's whatever its functionality will be wrong, right? So that's why 9 o'clock 20 this will be valid. At 9 o'clock 10 minutes this is valid, 9:20 this is valid, 9:30 this is valid. So 940 this will be valid. That is what, okay, I would like to say. Now if you know all these details, like what is the delay of each full adder, then what you do is give the input at 9 o'clock. Since we know that after 40 minutes we are going to get the right output, exactly at 9:40 I take the output from all the sum bits, then that is going to be the final answer for my 4-bit adder, right? So at 9:30 if you take, you get the wrong data. Okay, so we should be careful, right? And one more thing, there is a lot of delay. So full adder has to give the output here, that is this carry, then only this full adder works. And if this full adder gives carry, then only this works, right? In that way, so the last full adder takes lot of time to give the output. So finally, end of the day, so you get output after long time, right? Can we do any optimization? Already I told you, studying CO is nothing but optimizing the things, right? Optimizing the circuits, optimizing everything wherever it is possible. So here we can optimize it. So for that, we are going to study an adder called carry look ahead adder, CLA we say, okay? That I will be teaching you. So that carry look ahead adder doesn't require this kind of structure, so that delay will be minimized, okay? So every full I can say full adder is going to get the carry at a time. So how it is possible, sir? Without generating carry from this full adder, how this full adder works? So that is a trick. For that there is a logic, we will see that, okay? So carry look ahead adder is faster than this carry, ripple carry adder. One thing you remember. Second thing, so we'll try to calculate the delay with this ripple carry adder, because in the exam sometimes they give you ripple carry adder problem and they ask what are the delays. That means when you get carry and when you get some everything, okay? So we'll see that, okay? And one more thing, we can use this ripple carry adder or whatever the adder we are going to discuss, that carry look ahead adder also we can use for subtraction also, because there is no difference between addition and subtraction in this 2's complement arithmetic. Recall, so what is the difference between addition and subtraction? Addition is this one, right? Subtraction is nothing but x minus y equal to x plus minus y. You do addition like this only, but take minus 5 rather than y. Okay, so how to use minus 5 I will tell you. We have y, so how to calculate minus 5, otherwise how to create minus 5 I will teach you, okay? Let us see this circuit. So this circuit is going to represent addition and subtraction. Already I told you that. So if you have adder circuit, that is sufficient, we can do subtraction also. How to do addition subtraction? Let's recall. When you have x and y 4 bits, let's say 0 1 0 1 1 0 0 1, how to do addition? Addition is nothing but directly 0 1 0 1 and 1 0 0 1 to be added, correct? Yes, already we have a circuit for that, okay? Now what should be C naught value? Recall. So in carry look at ripple adder, did you remember? So the first bit C naught should be 0, correct? Because so here we have full adder, so we can implement this with full adder. So these two bits are nothing but x naught y naught and carry should be 0. So when I give 0, what is going to happen is, so this y naught, let's see. So y naught, this is XOR with, so I'm sending 0 now, okay? Because C naught and this C naught and this cable are same. So when you send 0, then 0 will go like this, here 0 and y naught. 0 and y naught will propagate like this to this through XOR gate. So y naught XOR 0, recall. So the formula for A XOR B is what? AB bar plus A bar B. AB bar plus A bar B. What happens? This y naught bit XOR 0. Y naught into 0 bar 1 plus y naught bar into B. B is 0. 0 into anything 0 plus 1 into y naught. So we are going to get y naught. That means what? Whenever it is addition, so 0 and XOR y naught, 0 XOR y naught gives y naught here. Similarly here y1, so on y3. So all that y naught, y1, y2, y3 will be added to x naught, x1, so on. Now if it is 1, C naught is 1. So what is going to happen, we'll see. First of all, we'll see the expectation. What are you expecting from this circuit? We are expecting subtraction. Whenever subtraction has to happen, then 0 1 0 1 to be added to 2's complement of y. Recall. So x minus y is nothing but x plus minus y. Minus y, we have y, but we want minus y, that is 2's complement of y. How to do 2's complement of y? First 1's complement, that means bitwise complementation, 0 1 1 0. This is one step. Then we have to add plus 1. So overall 0 1 0 1 to be added to 0 1 1 0 and plus 1. That means we have to add this one and plus 1, right? Recall. So we know this story. So this plus 1 is coming from here, okay? C naught, recall. Now when this 1 goes here, what is going to happen is 1 XOR Y naught. So let's do 1 XOR Y naught. 1 XOR Y naught is nothing but 1 into Y naught bar plus 1 bar 0 into Y naught. So 0 into Y naught 0 plus Y naught bar. So here you get Y naught bar, similarly Y1 bar, so on Y3 bar, and X naught X1 will be as it is. Second thing, this carry C naught supposed to be 0 for addition, but for subtraction the C naught supposed to be 1 because we have to add 1 also, right? So this 1 bit will be added. Okay, the first full adder, recall. So here we have a full adder. That full adder is going to take this 1 from here, this 0 from Y naught bar. Okay, so Y naught bar is nothing but 0. This C naught is 1. So automatically subtraction will be done. Right? So that's why this n bit adder can be used as adder and subtractor. Okay, so I can say that this is n bit adder come subtractor. Okay, of course it is adder, but we are using it as subtractor also. We have logic for subtractor here. This is adder only, carry look ahead, sorry, ripple adder or anything, whatever. So I don't want to fix it as ripple adder or anything. It's an adder. Now for this adder, the inputs we have to give properly. For addition, directly give x naught to xn minus 1, y naught to yn minus 1. For subtraction, give x naught to xn minus 1, y naught bar to yn minus 1 bar, and carry 1. So it will be like doing 2's complement followed by plus 1, correct? So that is the concept of addition subtraction machine.